The next speaker is Ibrahima, a research scientist in estimation modeling and analysis group. The presentation is about estimation and control of underwater optical wireless communication systems.
PDF.
All right. Thank you and good afternoon, everyone. So my name is Ibrahima. I'm a research scientist working with Professor Mariam Lalek at KAUST here. These last 2 days, we have seen amazing talks from diverse backgrounds, and I'm glad to see that my research vision aligned with this marine observation network. So before starting the title of my talk, so I would like to thank first the organizers, Professor Eric Ferrand, Professor Shinkyo Park, and Professor Pexito for this opportunity. So my talk today is about estimation and control of underwater wireless optical communication system. I will mainly focus on these 3 keywords: estimation, control, and optical wireless communications. So communications failures is actually one of the main factors of accident at sea, as you can see in this figure on this plot. So improper or communication breakdowns can lead to accident at sea, and it's both sides, it's for surface vessel and also for underwater vehicles. So we need to do something for that, and the best way is to address the spectrum scarcity in underwater by doing some remote communications, and optical wireless communication is actually optical wireless communication is an alternative for that. So the agenda of my talk, I would like to answer these 2 questions. The first question is, why should we care about underwater optical wireless communication? And the second question is, what estimation and control play for underwater optical wireless communications? As the audience has diverse background, in the first part, I will review the main advantage and practical challenge of underwater optical wireless communication across the state of the art of the optical link establishment. And in the second part, I will answer this question of what estimation and control play for this underwater optical wireless communication. And here I will highlight our research work on designing estimation and control algorithm for beam positioning and tracking, and estimation algorithm for light-emitting diodes. Underwater, let's start with the definition of underwater optical wireless communication. So it's a line of sight communication and unidirectional technology. Just unidirectional maybe makes the fact that you have some kind of challenge, but we need to deal with that. That use a modulating laser or light through the underwater or the sea to establish a communication link for several kilometers, and that provide also data rate of gigabits per second. So there is 2 configurations here, as you can see. There is a point-to-point line of sight configuration and a diffuse line of sight configurations. There is some other potential applications for underwater optical wireless communication, mainly some fish monitoring, coral reef also monitorings, and oil export monitorings. So the idea here is to expand the Internet of Things to underwater of things, to bring the Internet to underwater through the optical wireless communications. So if you look at most of the technologies that is used, actually is commonly used is acoustic technology. But this acoustic technology have some challenges, like the noise, multipath fluctuation, and latency. And mainly, it's have a limited data rate. So if you move to the optical fiber also, it can provide high data rate, long transmission distance, but it's difficult to install and maintain. And it's also limited mobility. And the seawater environment make it very complex. So now that's where the underwater play a role. So it has one of the advantages of this underwater optical wireless communication is the transmission speed. Okay, the low latency and the bandwidth. We are talking about transferring huge data rate. Okay, and you have also a license-free, longer transmission distance when you compare to the RF. And one of the main challenges of this underwater wireless communication is the alignment or tracking control. So we're gonna see how we're gonna manage this to the control and estimation. So the idea here is how can we design controllers to establish line of sight optical link in mobile platforms. So to know a little bit some insight about underwater optical wireless communication. So Professor Bunroy will give a talk later on at 4:15. So at that time, he will provide more information about optical wireless communication from a photonic point of view. So there is some challenge. And one of the challenges that came across this underwater optical wireless communication is the unknown movement of these underlying optical platforms. And some misalignment error that also do some vibration and turbulence effect and some uncertainties and disturbance in the underwater environment. So also if we refer to the control purpose, we need to get the states variables that we need to control. And this state of the system are not accessible, for example, the position and velocity. So there is a high requirement for good alignment and tracking control. So there is several approaches that are available to mitigate this problem. So I just cite some of these approaches. So mainly you can see some people mitigate this problem by dealing with the horizontal experimental tests. So they do the alignment, but it's horizontal. They are not doing it in a vertical way. And there is some also work that is done even in a no line of sight optical wireless communication. They don't use the point-to-point line of sight, but they refer to a no line of sight. And some others work on the performance analysis only rather than doing the tracking and the beam positioning. And as we can see, the mobile platform and the vertical communication are more challenging tasks. So some methods also do not address that the AUV, the autonomous underwater vehicle, may require to collecting and sending huge data. So it's important to refer that when we refer to the optical wireless communication, it's for the data rate. We want to change, we want to share or send more data those optical links. And so there is also a lack of a complete and efficient tracking control strategy in which the communication performance metrics are considered. So what we come up as a solution is to build an hybrid acoustic-optical communication links. Why it is important, this hybrid acoustic communication, Jim? Because of the range. We know that the acoustic provide a large range, like kilometers here, and the optical beam also is good in terms of bandwidth and data rate. So we think about combining them will be something very interesting. So we come up with this idea of bringing or bridging this hybrid acoustic optical communications. So now, let me start with the first part, which is with the second part, which is what estimation and control play for underwater optical wireless communication. So we focus now first in the control part for the beam positioning and tracking for mobile platform. As I mentioned, the mobile platform make it more challenging. So there is some key technical models that we maybe know from a control or robotic point of view. Is this key technical model is at the upper one, we have this simultaneous localization and mapping and navigation. So this is similar to the drone and self-driving car. And we have mature techniques for that to deal with this problem. So still there is some concern, but I guess we already have something enough to do with this SLAM navigations. So in the lower layer, we have the actuation and transmission. So the actuation and transmission also, we have enough to pull, talent pool, and we can buy some actuation is a reasonable price. So the crucial part here for the underwater optical vehicles is the control and estimation, and also the perception, perceptive. So because this guy we need to know a little bit about the model of the system. If you want the model of the dynamic, we need to know also a little bit about optimal control or trajectory optimization. So I will say also trajectory exploration. And we also need to know some dynamic programming, estimation, localization, engineering learnings, engineering, and some coding skills, and also computer visions. So really, we need a huge shortage of talents to make it really work. So now, what we come up as a solution is we develop an advanced model-based control strategy by incorporating a real-time acoustic localization system to guide the autonomous underwater vehicle towards the surface ship, because we want to do this. We want to do this tracking and alignment and pairing the surface vessel and the underwater vehicle. So the key consideration, so we first present the canal model for the acoustic and optical link to MATLAB. So what we want is not only to do the tracking of underwater vehicle, but we want also to evaluate the communication performance, optical communication performance. It's not we take an AUV and do the mapping or exploration. And the second, we estimate the direction error vector that is given by the acoustic based on the phase difference measured for we put 4 acoustic sensor nodes, and we develop model-based control for the AUV to follow desired directions towards the surface ship. And we test it through online simulations, both the control strategy and the acoustic one. So now, that's a flow chart in how it works. we have the surface vessel, and we have the underwater vehicle. So the idea is to use this hybrid acoustic communication to pair them. The acoustic will help to localize. But when we localize within a certain connectivity cone, we can send the optical communications because we have the possibility to have more data rate from the optical wireless communication. So what we do is, so now both of them are equipped with the transceiver. So they can send at the same time, they can receive the surface vessel and the underwater vehicle. So we thus perform the localization algorithm. And when we reach a certain cone, a connectivity cone, so that connectivity cone allows us to enable some optical communication. We do the tracking through acoustic, and we send, when we reach the code, we can communicate through the optical links. This is a zoom in on what I was saying right now. So there is a localization algorithm based on the phase difference. We use it to get this direction vector, and having this direction vector, we're going to feed it to the control, and we apply two types of control: a proportional derivative control and a adaptive control, like a model predictive control. And when we reach a certain connectivity cone here, that's a confidence level of the communication in which we can communicate through the optical communication. We go through the optical communication. So this is a block, a kind of block diagram to see how this is working as a feedback control. So we have a controller here, and we use this we apply these two type of control, a proportional derivative control and a model predictive control. So we have a reference noise. Here we have external disturbance, and we have also, these external disturbance are considered in the simulation also. And we have the plant, which is the AUV, and we linearize the model to the linear parameter varying model for the sake of implementations. And we use the measurement as a measurement. We rely on the localization framework. And we can have also some measurement noise that can act on the system. So what we want is to control the autonomous underwater vehicle. So we know that we know the model, and there is some direction that we need to control and velocity. And for the linearization of the model, we refer to an assumption here by keeping the reference a little bit constant in order to linearize the model and get this linear parameter varying model. So now, a unified view, here I'm proposing a unified view of underwater motion control. And this unified view of this underwater motion control can be seen as an optimal control. We can use a class standard control, but if you have a standard control that is a PID, proportional integral derivative, or proportional derivative control, we can always reverse this problem to an optimal control. And for me, a unified view of that, of controlling this underwater motion control, is from an optical control point of view. So here, so the optimal control, so you have to minimize a certain cost. This is your running cost, and you have a terminal cost here, and subject to a dynamic and constraints, and you have the states. So here in the models that we are controlling, we control the search direction, the sway direction that is given. If I come back here, what are the input? Because at the end we want to control the AUV. So we have we have the states are the search direction, which is in the X, the Y direction, we have the sway, and we have the yaw angle. And we have the linear velocity corresponding to this. And we control the shear and the yaw angle because it's under actuated systems. So maybe come back a little bit. So there is some challenge also to deal with this optimal control. And the main challenge is the nonlinearity that we get. The system is nonlinear dynamic, and the underwater environment is depend dynamically. Underwater environment is dynamic also. And we need for this model predictive control and any kind of optimization control, we need to be fast. We need to think about how the stock gonna go. And it may end up with some high dimensionality because of the states that you get for the models that you are dealing. So we use model predictive control, which has this residing horizon philosophy. So we use the dynamic model of the process. So model predictive is just follow 3 steps. At time t, you solve an optimal control of a finite horizon, and you apply the first optimal move, and at time t+1, you get a measurement and repeat the optimization and so on. It has this kind of advantage of repeating online optimization. It can be seen as a feedback. So now the optimization of the optimal optimization control is to minimize a certain cost plus a terminal cost subject to the models that we linearize, and so there's with some constraint also. So these are some tracking performance where we apply both PD control, this is proportional derivative control, and the adapter MPC. We call it adaptive MPC because of the linear parameter varying that is embedded in the model. So that's where this this adaptive model predictive comes. So as we can see in this plot, we do not only look at the tracking errors. Tracking errors with the MPC outperform, yes, the PD, the proportional derivative, but another factor that we look at more is the communication. How behaves the communication from the bit, from the logarithm of the bit rate, and also the pointing errors. So we disturb the model. We do some robust analysis by putting some ocean current force and measurement noise, and we can see also the transmission get lost with the PD control, the proportional derivative control, and the MPC is doing quite good here. So now this is another table that provides a comparison. So I'm out of maybe time. So the takeaway message is here we apply, we develop an adaptive, we apply an adaptive model predictive control combining with the localization approach. And we can see that this can achieve the state of the art for maintaining reliable hybrid acoustic communication in underwater environment. Okay, so I would like to acknowledge some of my team members that work with me on this paper. So now, that's the second part is the estimation. What estimation and control play, but here we use, we target more the estimation point of view. We want to do some estimation with the mobile platform. As you already know, so this alignment for maintaining a line of sight can be big challenging because of the environment and the turbulence and everything, the vibration. So the state also, if you want to do this alignment, we need to get access to the states. And here we develop an observer design to get this state. So what is briefly an observer design and how it's worked and why we are interested of this observer design. So observer is, as you can see here, is a herd of control systems. So you have a model, but you need observer in order to do any control purpose. We need to access to the states. If you don't have, if you have a disturbance, you can call it monitoring. And if you play more on the parameter, you can call it identification. So this is a scheme. Briefly, you have a plant and you need a correction term Non-observer is a copy of the system plus a correction term. And here we use a controller. So briefly, I will skip this because this is a motivation. So what I would like to share here is we come up with a fundamental result on us. We're not dealing only estimating the LED, but we propose a theoretical and fundamental result of the estimation purpose. So the high-level consideration is we propose a novel estimation-based trajectory tracking for this light-emitting diode. And the key consideration is we calibrate our own model for the LED, and we prove something on the no existence of a constant gain observer solution, and we propose a novel switching gain, and from that we can design a controller there. So now, if you look at this figure, we can see that you have a transmitter and receiver, but what you measure here is only the power intensity. Since you don't have the position, if you have to vehicle and velocity, you measure the power. So from this power, we made our space representation. And from we can discretize this discrete and get a discrete form. And this is done. And now what we prove is what we know. If you measure it, we have a single output nonlinear system, and this output is also output function is non-monotonic. So from this output, which is non-monotonic, we show that a constant gain observers does not do the job. So, and this proof can be done intuitively. The system is locally inobservable at the slope, and we need different sign of feedback gain. So intuitively, we know that there is a problem to build an observer here. So what we do is we use another measurement, which is a shifted angle. We use a shifted angle measurement to get off of this observability condition. So when we get this observability, we can actually build an observer. So that's what I present at the beginning, which is a copy of the system plus correction term. And this is a little bit math. So let me just I don't want to be out of the time. Yes. So we have an observer and we use some mean value theorem to because of the nonlinearity of the system, and we derive some error dynamic, and we have also some disturbance rejection here, and we develop a theorem for that. So this is, I can skip it. So now when it is done, we build a switching gain nonlinear observer because we need to solve this problem. And one solution is a switching gain, a gain that switch between different regions. This is what has been done here. And the simulation was working well. And we compare the simulation, we compare actually with the extended Kalman filter, and we show that we are better than the extended Kalman filter in terms of estimation. So now the takeaway message here from this estimation part is we prove the no existence of a constant gain observer gain for this problem, a specific problem of this LED. And we propose a novel switching gain observer design, and we demonstrate the stability of the overall switching gain observer. And we extend this work also for a cyber physical system where we have some jamming, some attack like the jamming signal that interrupts the signal. And yeah. So now in general conclusion, so we actually underwater wireless communication system have bright futures to address the spectrum scarcity, and also optimal control provide a unified view of underwater motion control problems. And as you can see, estimation and control are also enabling technology for autonomous underwater vehicle. Specifically, if we use optical communication, that is actually not really used. And the future of mobility, how I can see my vision of the future of underwater mobility. So here, what I was talking was more estimation and control, but there is a way to bring it up to the distributed cooperative. And we have seen here some amazing talks that highlight this factor of distributed cooperative. So this distributed cooperative, I believe, are key enabling technology for underwater Internet of Things and the future of underwater mobility. But it has also some different challenges: trajectory optimization, perception, safety, and also the use of optical communication, and also the collision avoidance. You have to deal with this challenge. And for that, you need a huge shortage of talent to deal with that. So I would like to acknowledge my previous group members, actually, and Assam is there, actually. So thank you, and I'll be happy to take some questions.